No, you're not wrong. We skipped section 4.2. We'll go back and pick it up later because I'm just anxious to get to curve sketching because it's lots of fun. This section is all about how derivatives affect the shape of the graph. It's more like what derivatives tell us about the shapes of the graph. What does f prime say about it? Well, it's the slope of the tangent line. So if the tangent line is positive, your graph is going up. If the tangent line is negative, your graph is going down. If the tangent line has a slope 0, then your graph has a little flat spot, either a max, a min, or just a little flat area. So, positive tan line, negative tan line. Here's the increasing, decreasing test. If the derivative is positive, then f is increasing. If it's negative, then f is decreasing. Let's look at a quick example. Example 1. We have f of x is 3x to the 4th minus 4x cubed minus 12x squared plus 5. So first thing I'm going to do is take the derivative. 3 times 4 gives me 12x cubed minus 3 times 4 still gives me 12, this time x squared. 2 times 12 gives me minus 24x, and I'm done. Now, first thing I'm going to do is set this equal to 0 so I can figure out where it's positive and negative. So I'm going to factor a 12x out. That leaves me with x squared minus x minus 2. And two numbers whose product is negative 2, whose sum is negative 1, minus 2 plus 1. So 12x equals 0, x minus 2 equals 0, or x plus 1 is 0, x is 0, x is 2, or x is negative 1. So I'm going to draw myself a little number line. They don't have to be spaced out properly, they just have to be in the right order. So I'll put negative 1, so I want to write it on top, 0, and 2. Not that important right now, but I usually like to label them up top. Now, I'm going to go ahead and do a sign chart for this one. So we have x minus 2, we have 12x, I should have written that one first, and we have x plus 1. So x minus 2, if I plug in something less than negative 1, it's going to be negative. Something between negative 1 and 0, negative. Something between 0 and 2, negative. Finally, bigger than 2, it becomes positive. This is going to be negative when x is negative, positive when x is positive. If I plug negative 2 into x plus 1, I get a negative thing. If I plug in something between negative 1 and 0, I get a positive thing, and it can't change its mind. So if I look at the product here, negative times a negative times a negative. So my function is going to be decreasing, increasing, decreasing, increasing. And that makes sense because we have a fourth degree polynomial with a positive leading coefficient. There, now I can point at it, a fourth degree polynomial with a positive leading coefficient. That means its ends go up, so it's decreasing, then it's increasing, decreasing, then increasing. It looks something like that, except a lot more precise. So here's our pretty solution. There's the sign chart that tells us where it's decreasing, increasing, decreasing. So you can use your sign chart to write down your intervals, negative infinity to negative 1, negative 1 to 0, 0 to 2, and 2 to infinity. And there's the pretty graph. Now let's talk about local extreme values. Local extreme values are where your derivative changes sign, because it's where you change from increasing to decreasing or from decreasing to increasing. That brings us to the first derivative test. Suppose you have a critical number of a continuous function. We learned last section that critical numbers are where we start looking for maxes and mins. If the derivative changes from negative to positive, and I always draw it in the air, if we go from negative decreasing to positive increasing, then we have a minimum. If we go from positive increasing to negative decreasing, we have a maximum. There's the pretty picture. Greater than 0, less than 0. Derivative less than 0, greater than 0. Now, just because the derivative is equal to 0 doesn't mean we have a critical value. Remember, you could just have a flat spot in your graph. Now let's look at a couple of pictures here. On the graph of the derivative of a function, so we have f prime of x. We want to look at this and see where our original function is increasing or decreasing. So I'm going to go ahead and draw a little sketch of that one for number 5 because it's easy. It crosses the axis at 1 and again at 5, and then it ends at 6. So let's see if I can play connect to the dots. No, because it was supposed to cross the axis at 5. We'll do it this way. This is 5. This is 1. Okay, so I could make a sign chart from my graph here, like some of you had to do for the acceleration and velocity problem on the last test. Negative, positive, negative. So my derivative is negative, then positive, then negative. So it is decreasing from 0 to 1, and again from 5 to 6, and it is increasing from 1 to 5. Here at 1, it changes from a negative derivative, decreasing, to a positive derivative, increasing. So that means it's the location of a local minimum value. At 5, it changes from positive derivative, increasing, to negative derivative, decreasing. So this is a local max value. Now I'm going to let you do number 6. We'll catch up in a minute. Okay, you didn't have to watch me struggle to try to draw this picture. I drew the picture and then I put the numbers in to make sure it matched correctly. But we are positive, negative, positive, negative. Increasing, decreasing, increasing, decreasing. We change from increasing to decreasing. Local max. We change from decreasing to increasing. Local min. And again, local max. I won't make the funny sounds again. Okay. Example 3. Find local max and local minimum values of the function on this particular interval. Example 3. We've named it g for a change, is x plus 2 times the sine of x, and we're going from 0 to 2 pi. So just one cycle of sine. G prime of x would be equal to 1 plus 2 times the cosine of x. I set that thing equal to 0. Subtract 1 from each side. Divide. And cosine is equal to negative 1/2 when I have a pi with a 3 in the denominator, and when it's in quadrants 2 and 3, so 2 pi thirds and 4 pi thirds. So I'll make myself a little sign chart. I start at 0, 2 pi over 3, 4 pi over 3, and 2 pi. Now you can logic your way through it. You can also make use of your technology. Let's make use of our technology. Table, edit function, clear out the old stuff, and let's put in our derivative. 1 plus 2 cosine x. And make sure I'm in radians. Yes, indeed I am. So first I need something between 0 and 2 pi thirds. So let's just put in pi thirds. That gives me a positive thing. Now I need something between 2 pi thirds and 4 pi thirds. I think pi will do that one. And that gives me a negative thing. Now I need something between 4 pi thirds and 2 pi. So I'm going to go with 3 pi halves. You could have gone with whole numbers, but once I start thinking about pies, I just stick with the pies. So we are increasing 0 to 2 pi over 3, and from 4 pi thirds to 2 pi. And we are decreasing from 2 pi thirds to 4 pi thirds. Label this one as increasing. We change from increasing to decreasing. So that means we have a local max at 2 pi over 3, and let's see what the y value would be there. So I would have to go back to the original function and plug in 2 pi over 3. So let's look at g of 2 pi over 3. would be equal to 2 pi over 3 plus 2 times the sine of 2 pi thirds, sine of 2 pi thirds, so 2 pi over 3, and the sine of 2 pi over 3 is square root of 3 over 2. Then it continues to decrease. At 4 pi thirds, it starts to increase. So it changes from decreasing to increasing, which means I have a local min. The x value is 4 pi thirds. The y value would be 4 pi thirds. Oh, I forgot to multiply that by 2, didn't I? Yes, I did. So that should have just been 2 times square root of 3 over 2. So that should just be square root of 3. And this will be 4 pi thirds minus square root of 3, because sine of 4 pi thirds is negative square root of 3 over 2. 2 times negative square root of 3 over 2, negative square root of 3. So here's the pretty solution. And there's your answers as decimals. Local max, local min. There's the nice picture. So, another good use for sign charts. I like sign charts. They organize things for me.